All right, so last class we were introducing some compounds, or some terms that we need to understand to speak effective chemistryese to each other, right? And one of those terms was atom. And an atom, when we talk about atom, what needs to come to mind is a nucleus. And what's in that nucleus? Do you remember, Tom? Very good. Protons and neutrons in the nucleus. And what is surrounding it on the outside? Very good. And if, let's say that this proton, or this nucleus here, let's say there's 7 protons in PRT, oops, I misspelled that. There's 7 protons in the nucleus, all right? If that's the case, if there's 7 protons in the nucleus, then can we know which atom, what kind of atom that is? Neutron. Not neutron. What does that say there? Nitrogen. Nitrogen. Very good. Nitrogen. Excellent. So an atom is a nucleus with electrons around it, and the number of protons helps us know what kind of element it is. Very good. A compound, and we're going to talk a little bit more about the term compound here. Compound is a combination of different atoms to form a new material. All right? And we gave some examples of compounds last time. We said one example was water. This is a compound because it has 2 different kinds of elements in it, right? Carbon dioxide was another example of a compound. This compound is called sodium chloride. It's also another example of a compound, all right? Now there's also further classifications of compounds. So if I were to say that everything in my circle here are different kinds of compounds, there are 2 major classes of compounds that we're going to be dealing with in this class, all right? And those 2 types of compounds are what we call molecular compounds. So all of these would be our molecular compounds. And then the other kind is called ionic compounds. All right, ionic compounds. Now, for now, the way that you'll be able to tell a molecular compound is it's made of non-metals. Only non-metals in it, no metals. Whereas an ionic compound has metals and non-metals. All right, so all of our compounds can be split into 2 different classes, 2 different groups, molecular compounds and ionic compounds. Now, all we have to do is look at the compounds, so here's some examples of compounds, and see whether they have a metal or no metal. Because if it has metals and non-metals, then it's ionic. If it has no metals, then it has to be molecular. But we haven't talked about how we can tell by looking at the periodic table whether it's a metal or a non-metal. So we have to know how to do that. And here's how we do that. The metals and the non-metals, for the most part, are separated by this green staircase. Everything on the right side of the green staircase, those are our non-metals. Everything on the left side of our green staircase are our metals. The only exception is this top left one, which is hydrogen. Hydrogen is also a non-metal. Okay, so you have different compounds here, H2O, right? We have our periodic table here. Let's see if you can tell whether H2O, what kind of a compound it is. Is it a molecular compound or an ionic compound? What do you think? What is water?
Molecular.
That's right, molecular. Very good. How about CO2, carbon dioxide? It's molecular, right? Very good. It's molecular also. How about this one? Sodium chloride. Sodium chloride. Here's a hint. Sodium is element number 11, and chlorine is element number 17. Is sodium a metal or a non-metal?
Non-metal.
Here's number 11, sodium. Is it on the right side or the left side of the staircase?
Oh, left side, so it's a metal.
Metal. Very good. So that means we know right away sodium chloride must be what kind of a compound? Ionic. Ionic. Very good. It's an ionic compound. So we have molecular compounds and we have ionic compounds. Very good. And we can tell by looking at the periodic table where our nonmetals are, including hydrogen over here, and where our metals are, everything else. So most of the periodic table is what? Metals or nonmetals? That's right. Most of the periodic table is metals. All right. Very good. The other type of material that we talked about last time are what we call are just elemental or elements, right? Compounds that are elements are just a single kind of atom. Now, my ring. What do you think my ring is made of? What do you...
Iron.
No, it's not made of iron. My ring is a gold ring. It's made of gold. All right. Now, it's not actually only made of gold. There might be some other, there's definitely some other elements in here, because if you just have a single metal, like gold, then it's really easy to bend. And so they don't make jewelry of just a single metal. They usually mix the metals together. But if we pretended that my ring was made of gold, then we could say it's all gold, it's elemental, right? Elemental. That means that it's all the atoms are the same. Do you know how many protons an atom of gold has? Can you tell me how many protons an atom of gold has? No, here's gold, AU, right here.
79.
Very good. That's how many protons an atom of gold has, because that number indicates the different protons in that type of element. So, things like gold, sodium by itself, right? Iron. So this is a different way of having materials, right? You can have elemental materials, all right? You can also have elemental materials that are molecular in nature because they go around in little groups, like O2, oxygen gas, or N2. They're both nitrogen, but they don't go around in single atoms. They go around in pairs like this. So O2, N2, Cl2, F2, these, because they go around in little groups of pairs, are called molecular. Molecular. The word molecular means it travels around in little packets, little groups. So these compounds are molecular, but they're compounds, so they're made up of more than one kind of element. These elements here are only made up of single elements, but they might go around in little packets, like molecular packets, so we could say they're molecular as well. Okay? Now, we're going to talk about two other terms. A chemical reaction, and to introduce a chemical reaction, the term chemical reaction, whatever that means, we're going to talk about it. We also have to kind of introduce what a physical reaction is. All right? And now we have ways to write the state. Have you ever heard of the different states that elements can be in, like solid? What happens if you heat a solid? What does it turn into?
Liquid.
That's right. Very good. And if I heat a liquid a whole lot, what does it turn into? Gas. And that's what these little letters mean to the right of the material, either elements or compounds. So if I have something like this, Au solid, what did Au stand for? Do you remember?
Gold.
That's right, gold. And I heat the gold and make it a liquid. What do you call that when you make something a liquid by heating it from a solid to a liquid?
Melting it.
That's right. I've melted it. I've melted this species. Now here's a hard one. Do you know what you call it when you make something that's a liquid into a gas?
Evaporating it.
Okay, evaporating or boiling. Very good. Right? Excellent. So, these are called physical reactions. They're not chemical reactions because I'm not changing how the gold is interacting with different elements. It's still just gold, but it's in different phases. So this is an example of a physical reaction. Okay? A chemical reaction is one in which I have one kind of element, another kind of element, and I bring them together and I form a new compound. Now, the hydrogen and oxygen are interacting with each other, whereas before the hydrogens were by themselves and the oxygens were by themselves. Okay? So this is not a physical reaction, but what kind of a reaction is it? Chemical reaction. Very good. A chemical reaction. And we can tell it's a chemical reaction because the elements are now interacting with each other differently than they did before. Some other terms that we want to be familiar with. This side of the arrow of our reactions, whatever's on the right is called the products. Whatever's on the left is called the reactants. The things that are reacting together to form the products. Okay, very good. So we have chemical and physical reactions. Physical reactions are pretty easy to see because generally, like in this case here, what am I doing when I go from liquid water to solid water? What do we call that process?
Physical reaction.
It's a physical reaction. Very good. And specifically, what do I call it when I take a liquid and I change it into a solid? What do I have to do that?
Freeze it.
That's right. I'm freezing it, getting it really cold, slowing those molecules down, and so they stick together more tightly and they become a solid. Excellent. Now, chemical formulas, like these ones here, are helpful to us because they let us see how many different kinds of atoms are in the compound and also how many of that given kind are in a compound. So here's our water, H2O. Here's a compound, FePO4, NaCl, H2SO4. Let's see if we can test how well you remember. If we look at FePO4, this one here, is that one a molecular compound or an ionic compound? And we'll put that FePO4 in the corner there, and we'll bring back our chart here of molecular or ionic compounds. We'll also have to look at this, FePO4. See if you can find the elements on the periodic table and tell me whether it's a molecular compound or an ionic compound.
Where's PO?
P and O are separate elements. P is phosphorus and O is oxygen.
It's ionic.
It's an ionic compound. Very good. It has a metal, iron, and some phosphorus and oxygen, which are non-metals. Excellent. Very good. So, we can also, let's use this other chemical as an example, H2SO4. If we use H2SO4 as an example, H2SO4, can you tell me what kinds of elements we have in this compound? Hydrogen. Oh, we need the periodic table to help us out, huh? Let's see. What is S? What is S?
Are you looking at the periodic table right now because you froze?
I froze.
Sulfur.
Very good. So we have hydrogen, sulfur, not sodium, and what is oxygen? Or sorry, O is oxygen, isn't it?
Yeah.
Now, this, because sulfur, is sulfur a metal or a non-metal?
Not a metal.
Very good. How about oxygen? Metal or non-metal?
Non-metal.
Now, how about hydrogen? That's kind of a tricky one.
Non-metal.
Very good. So because we're dealing with only non-metals, what does that tell us? What kind of a compound do we have? What is H2SO4? Do you remember that name?
It's not metal at all, or only metals?
Nope, there's no metals. Only non-metals, right?
Molecular.
Very good. Molecular. We got a molecular compound. Excellent. Now, let's look back at our H2SO4. And how many different kinds, or sorry, we said we had hydrogen, sulfur, and oxygen, right? How many hydrogen atoms are in one unit of H2SO4? 2. Very good. How many sulfurs? 1. Very good. And how many oxygens? 4. Excellent. Well done. Now, I'm going to introduce something new using that same compound, H2SO4. Sometimes we'll put a number in front. That number is called a coefficient. A coefficient. And what it's telling me is that I have now 3 of these whole things. 3 of those. So if I said, how many hydrogen do I have altogether? Could you tell me? Very good. 6. How about sulfurs? 3. Very good. And oxygens? 12. 12 oxygens. Excellent. Now you don't want to be confused and think that this 3 only refers to 3 of these or this part of it. It's 3 of the whole thing, right? Excellent. Now, as we mentioned, some elements go around in little molecular packets, like hydrogen, oxygen, nitrogen, chlorine. They go around and not as just a hydrogen, for example, but they go around as H2. Or oxygen is elemental. Its element is molecular. It's a molecular element. Goes around in little packets of 2. Okay. Another thing that we want to recognize is that sometimes chemical formulas might be written more than one way. So here's a compound, this one here, CONH2, and then you see the NH2 portion is in parentheses, and then there's a 2 after that NH2. All right, so we say CONH2, and that there's 2 of those NH2 portions. All right, so now we want to determine how many carbons there are in one of these units. Can you tell?
1.
That's right. How many oxygens?
4.
Nope, there's just 1, because this 2 here is just telling me that there's 2 of this group. So there's 1 carbon.
I thought oxygen was H2 was helium.
Oh, this is hydrogen. H is hydrogen. This is oxygen. So there's nitrogen and hydrogen. How many nitrogens do I have in this statement?
2.
2. Very good. How about hydrogens?
4.
4. Very good. 4 hydrogens. Now, if I write the compound differently, CON2H4, right, I can see that the number of carbons, number of oxygens, number of nitrogens, and number of hydrogens are the same, aren't they? Can you see that? And the reason why somebody decided to write it like this is because, as you can see, the molecule itself, I'm going to write it here for you, CONH2, looks like this. So it's like we have a CO group and 2 of these NH2s. And so when somebody writes it like this, it's kind of helping us imagine what the structure looks like. So we won't talk about that a lot until later, but we don't want to be concerned. All right, so just because the chemical formula might be written slightly different, we don't want to be confused into thinking that they might be different compounds. They could be the same compound. You can't necessarily tell simply by the chemical formula always. All right. So now we're going to introduce to you a different kind of compound. It's not really a different kind of compound. It's still the same type. And let's see if you can tell. What kind of compound is this CuSO4, which we call copper sulfate? If we bring our periodic table over here, can you tell me whether this is an ionic or a molecular compound? Ionic, that's right, because copper is a metal. So we have this ionic compound. Now sometimes compounds ionic compounds more specifically, they absorb water. And I don't know if you've ever seen that, but like salt shakers in Hawaii, they put something in the salt shakers besides just salt. Do you know what else they put in there?
No.
They put in little pieces of rice in the salt shakers. And what that does is the rice helps absorb some of the water. If you don't do that, then the salt will absorb the water and will clump up. And it'll be hard to come out of the salt shaker. The little holes will get clogged and it won't work anymore. This property of absorbing water from the atmosphere, from the surroundings, is called hydro for water, scopic, meaning kind of scraping and scavenging, hydroscopic. So it will suck water from the surroundings. And when this happens, your ionic compound will become hydrated, which is a fancy way of saying it'll absorb water. Okay? So hydrates are ionic compounds that have some water with them. And here you see copper sulfate, CuSO4, and the hydrate will be indicated by putting a dot, a big dot like this, and then writing how many water molecules, 5 in this case, for every unit of copper sulfate. Now if you take this hydrate, put it over a flame like this, all the water will heat off and you'll be left with just copper sulfate. All right? But sometimes when you buy copper sulfate or different ionic compounds from the chemistry store, you'll buy them as hydrates. So like this compound we call copper sulfate penta. Penta is the fancy word for 5. It's the Latin prefix for 5. Pentahydrate, meaning that there's 5 waters. So the name of this compound is copper sulfate pentahydrate. Penta meaning 5. Now, why would you buy a compound like copper sulfate as a hydrate? Why would you buy it like that? Well, here's why. If I just went to the store and I bought a container of copper sulfate, if I didn't have any hydrates on it, that's fine. There's the lid. And whenever I open the lid, if I remove the lid and take it off, then what happens is water molecules, H2O, they will come in from the air and just stick to the salt, to the ionic copper sulfate on the surface. So I take the lid off, I take some copper sulfate out, and then I put the lid back on. But now when I put the lid back on, I let some water in there, and so now the surface copper sulfate isn't just copper sulfate anymore. It's copper sulfate with some water, because copper sulfate is, do you remember that fancy word? What did I say? Hydro what? Hydroscopic. Yeah, hydroscopic. What does that word mean? Do you remember?
It's when,
It does what to the water?
it makes it, it absorbs it.
It absorbs it. That's right. It absorbs the water onto the surface. So if I open this lid my second time and go to get some copper sulfate out, I'm not going to get copper sulfate at the very top, am I? I'm going to get copper sulfate with some hydrates. And I don't know how many hydrates got on there. X, I can just say, because I don't know how many. But every time I open it, there's going to be more and more water stuck on the surface. So you don't like to buy, generally, compounds, if they're very hydroscopic, you don't want to buy them with as anhydrous. Anhydrous means without water. You want to buy them as hydrates, because when you buy them as hydrates, what that does is it allows you to know exactly how much water there is, and so it won't gather water over time. So here we go. If I say I have 1 unit of copper sulfate pentahydrate, if I have one of these, how many water molecules do I have for every unit of copper sulfate? How many water molecules do I have for every unit of copper sulfate? That's right. I have 5. And in this whole thing, how many coppers do I have? 1. Very good. How about sulfurs? How many sulfurs? 1. Very good. Now here's a tricky one. How about oxygens? How many oxygens do I have? 9. Very good. 9. Here's another tricky one. How many hydrogens do I have? 10. Excellent job. Okay. Here's your last tricky one, and then we're done. Here, this time, I'm going to say I have 3 of the copper sulfate pentahydrates. So, same thing. Copper, sulfur, oxygen, and hydrogen. How many coppers does this represent? Wait, is it 3 all of them or just the first one? It is. It's all of it, like that. All of that. Copper's 3. Yeah. Sulfur's 3. Sodium's 3. Sulfur. It's sulfur. Good. Sodium's 3. You know what I just noticed? I wrote down 5 somehow. I don't know. But you said sulfur was 1, and that's the right answer before. So just in case somebody caught that. Sulfur was 3. How many oxygens now when I have 3 of these? Maybe it's easy to do it without the 3 first. What did we have last time? 20. No. How many did we have last time? Well, we had 9 last time. So, 12. No. Not plus, but times. 9 times 3. It's 22. 27. 9 times 3 is 27. Very good. So let's see if you see how we got that? Yeah. Okay. How about hydrogens? How many hydrogens do we have this time? 30. Very good. Excellent job. And it becomes very important for us to be able to count how many elements there are in the given statements like this. Now remember, do you remember what we called that number in front? I'm going to write it down here. Coefficient. That's the coefficient in front. And that means we have 3 of everything that's there. Very good. You did an excellent job. I'll see you again next time. Bye-bye.